the first essential piece of information related to Gauss's law is the concept that when we're dealing with Gauss's law, there are two sides to the description of what Gauss's law can tell you. There's the part about how much charge is enclosed in my surface, and there's the part that's about the flux passing through the surface. So as an essential thing about Gauss's law, you have to understand what flux is and what the limitations of knowing flux tell you. Flux isn't the electric field. Flux is the sum of the electric field that passes through an area. Again, flux isn't the electric field. It is the sum of the electric field that passes through an area. And although it's come up, you need to be reminded that its units are still based on the unit of electric field and area. So that's newtons per coulomb times meter squared is the unit of flux. Now, when we talk about enclosed charge for Gauss's law, we are talking about the net charge. That's come up in a bunch of questions too. That we're summing up the total charge enclosed by our Gaussian surface. So, of all of our discussions about Gauss's law, it really isn't about electric field. It's about flux, and it's about enclosed charge. We can use it to tell us about electric fields, but that's not what the law is about. Principally, the law is telling us that the amount of flux any region of space has is related to the amount of charge in that region of space. We had specific questions that were related to what it meant to have a Gaussian surface and charges on the outside and charges on the inside. Without having values to these charges, I think it appropriate to remind you that all four of those charges contribute to the electric field in the space. Meaning, if I want to know the electric field at this point on the surface, all four of those charges contribute to the electric field there, because they would all contribute to a force on a charged particle there. Gauss's law doesn't tell us anything about how these charges contribute to the electric field at the point P labeled. That's not what Gauss's law is about. Gauss's law will tell us that those 2 points don't contribute any net flux. That if they're outside the surface, their field lines pass into and then out of the surface. They don't contribute net flux. The only points that can contribute net flux are points that are inside the surface. And I think that the AP exam is going to try and confuse you on that point. I think they want you to be confused. And the reason they want you to be confused is because of the third thing that is important about Gauss's law. That in situations that are symmetrical, we can use Gauss's law to find electric fields for unique situations. That's not the intent of the law, but it is a use of the law. That in situations where we have the appropriate amount of symmetry, we can use this law to figure out the electric field. That's the third point about the law. The problem with that conversation is that it assumes something, that you could always find the electric field using this law, and that's not true. That we can only do this in situations where the electric field is uniform about the area. In any other circumstance, if the electric field and the area are in some way changing, then this is often a calculation that can't be made. either because we chose a poor shape to our surface or because there is no surface that has the proper symmetry. So, an example. If I have a partial horseshoe of charge, a charged rod that's been bent in some shape, I can't wrap a Gaussian surface around that would allow me to pull the electric field out of the integral. I mean, Gauss's law still applies. There is a Gaussian surface that I can place here that will tell me how much flux this bar produces. Meaning right now, the amount of flux that bar produces is that. That doesn't tell me anything, but Q enclosed equals epsilon times the flux. So if I wrap a surface around it, I can tell you how much flux there is. And it wouldn't matter whether it was this surface or that surface, they have the same amount of flux. Why? Because they have the same amount of charge enclosed. An excellent trick question, by the way, to give you two really bizarre and different surfaces, but as long as they enclose the same amount of charge, they would have the same amount of flux. And going back over here, if these four charges were the same value, and I tell you that, well, we have two different Gaussian surfaces. Do those two surfaces have the same flux? They sure do. They enclose the same amount of charge. In fact, they have the same amount of flux as this surface over here. Closed charge, 0 in all three of these surfaces. Right? Net charge. So they all have the same flux. So I'd argue again that Gauss's law seems like it's this powerful law, and it is. But if I want to trick you, I get you thinking about electric field and then ask you about electric flux. Flux is charge enclosed. It's always easiest to look at the charge enclosed than it is to calculate the flux. Now, there are 4 use cases for finding the electric field using Gauss's law. And I believe we saw every one of the use cases. This is me leaving out the point charge, but the point charge, I guess, is a 5th use case. We did the point charge. I didn't want to include that one because I thought that was too rudimentary and simple, because it's kind of superseded by the charge sphere. The charge sphere is an excellent use case. Whether a conductor or an insulator, the charge sphere is a great use case for Gauss's law. It has proper symmetry to allow us to use both a Gaussian surface that is outside the sphere and inside the sphere. So for insulators, we have to be careful about how much charge we enclose in our sphere, because sometimes we're only enclosing a piece of the inside amount of the sphere. So we need to be aware that it's about the amount of charge we enclose. You guys remember that conversation, I hope, from a couple of weeks ago. But for conductors, being inside just means the electric field is 0. Again, it's an excellent use case for Gauss's law is the sphere. The next use case for Gauss's law, the infinite line, right? The line of charge. Any line can be infinite if you're close enough to it. So a bar can be infinite if you're close enough to it. And we talked about the fact that the infinite line and the infinite charge cylinder, very similar case scenarios, but allows you to have a surface that you can be inside the cylinder, but it's still a good use case scenario. If you remember, this is what gave us the electric field near a line of charge. Nope, there's no, it's art, right? I think the pi goes away. There's no pi there. Yeah. And then we had, of course, the big sheet of charge. Another use case. The sheet of charge, where we found that the surface density gave us the electric field equal to something like that. And the reason a sheet of charge is important, and I want to reiterate this, is that it's a uniform field. The field itself does not change as you get further away from it. So if we want to produce a uniform field, a sheet of charge is the way to go. Lastly, the other use case we had was near the surface of a conductor. Now, ultimately, I'm wanting you to understand that that's how we use Gauss's law, but the use cases are pretty limited. That doesn't mean they can't throw at us something that's bizarre, and they have. I am not looking to do anything bizarre on your test. You're going to get a standard question. It's either going to be an infinite line, a couple of concentric spheres, something like that. We will explore some of the weirder questions, but I want to make sure you have a pretty solid grasp on these first. And note that there is some other stuff out there. I also, though, want you to remember that there are ways that you can get tripped up that have to do with this. First, just a reminder that our point charge equation for the electric field, which we also apply to a sphere now, because we know that a sphere has a similar equation for electric field, is derived and has different meaning than the point charge equation for the electric potential. We tend to apply them the same way, and that's wrong. This is about a point in space. This is about work getting to a point in space. And will trip you up if you're not careful. Remember, we talked about that. If you have 4 point charges, and I ask for the electric potential at the center, no big deal. You can apply this easily by just adding up the 4 contributions to the electric potential. But if I have a nope. There. If I have a conductor and a point charge, and I ask about the electric potential here, you better be very careful how you use that. I'm not sure you could just figure out how far apart these are and use that relationship for the electric potential. Because I can't go from here to here without going through a region of space that has an electric field of 0. So remember, this can only be used if there is a pathway from infinity to that location in space that you're interested in finding the electric potential. Go ahead.
So I don't know if this will sound stupid or not, but when you have like that conductor ring outside of a point and you're like pushing, like or not pushing, but you're putting the work that you need for like potential, could you like think of the ring or the space where the field is zero as like resetting the work or like the energy? Like so you start from
I would say it's pausing, not resetting.
oh it's pausing.
Yeah, because if this particular question is one of the ones that I think intentionally gets put on the exam to try and ensure that people understand electric potential. So if I was to zoom in on it a little bit, and I'm trying to keep it all as symmetrical as possible. So everything here concentric, is that all right? Now, if I say this is A and this is B, the electric field right here, just at the edge of the outside of the shell, the electric field has to be Q over 4 pi epsilon naught B squared. You okay with that? And I also know that the inner edge of the conductor will have charge negative Q, and the outer edge of this conductor will have the charge positive Q. That has to be true as well, because we know that the positive charge on the inside will pull an equal amount of charge, so that when I do a Gaussian surface inside the conductor, I can show that the enclosed charge is 0. All of that sound familiar? So if I say all of those things to you, is that enough to remind you then that the electric potential at this point would have to be Q over 4 pi epsilon naught B squared? Because there is a direct path from infinity to a place right on the outer edge of that conductor.
Would it be B squared?
Oh, sorry, just B. Because there's a pathway from infinity to that point right on the outer edge of the conductor. But it pauses. When I go into the conductor, there's no electric field, so it takes no work to go from this side of my conductor to this side of my conductor, because there's no field inside. So that suddenly means that the electric potential right here would also be Q over 4 pi epsilon naught times B. The electric potential has to be the same on the inside and the outside of the conductor because there's no electric field inside.
And then when you just add like the electric potential from like A away into, does that make sense?
Added to what?
Like if you're finding the electric potential at Q, like the
Like if I wanted to go inside here someplace and find the electric potential, say right there,
yeah.
I'd have to do the integration.
Oh, okay.
I would have to do, to find from, and you wouldn't, you could subtract. But what I mean by that is you would have to find the difference in potential from here to here and then add it to this.
Oh, okay.
So that likely means something like this. Let's say this is a distance r away. You would have to then do E dot dr from A to R. That would just be the change in potential. Now, they haven't asked this ever, but I think it's a good question because you should be able to figure out this potential, and then you would have to calculate the change in that potential and then add it back to a potential you had. Again, I don't think they'd ask that question because that's a lot. To me, that's top level understanding. And even now, that's a hell of a lot to ask of a student, I think. I think asking for this potential here, very reasonable. I think that's very reasonable. I think asking for the potential of another point inside, I think that's broaching on unreasonable. Now, are they going to ask unreasonable questions? Yep, they are. They have. What do I think this is? I think this is letter F on the last question of the FRQ. You know what I'm saying? Like, you get that question, fine, don't get it. You're still getting a 5 if you got everything else right to get to here. But you're not going to get these last 3 points. Does that make sense?
Yeah, and when you do like the integration for potential, like I know we covered this when we first covered potential, but how do you know like if the dot product's positive or negative?
It's the direction of the electric field compared to the direction of R.
Oh, gotcha.
So R is a line drawn from your point to the place you're going. So, and E, of course, is just the direction of the electric field. But I have every intention of coming back to this once you guys advance a little bit more and we're not as scared of what the electric potential actually means. We went through it really fast the first time, and we were very careful to talk about direction and the dot product and all of that and doing the line integral. But for everybody, their brains were all whirling because we had just done all those other continuous charge distribution things. So we went through a lot of that because it was pertinent at the time. But we'll come back to these when this stuff is like old news. So probably not till February. All right.